This is Ms. Hurtado, and today's lesson is going to be on plate tectonics and Earth. Some of the things that we're going to discuss is how the rock cycle, plate tectonics, volcanoes, and earthquakes shapes our lithosphere. And then we also want to be able to predict the locations of volcanoes, earthquakes, and faults based on the information in a variety of maps. So your objectives are to learn the classification of rocks, what Earth's internal structure is like, the theory of plate tectonics, and we're going to discuss plate boundaries, how they move, what the results of that movement, that movement is, some real life examples of landforms that we see as a result of the movement of plates, and what hazards can come from them. So the first thing you're going to want to do is go ahead and click on this link. This will take you to a USGS, which is the United States Geological Survey, and it's going to take you to an earthquake map. So when you pull up the link, this is what you're going to see. It's going to zoom into an area of the United States, and the first thing you're going to probably notice are what those little circles are, the red and the orange ones. These are actually locations of earthquakes. So go ahead and take a minute, and then you can see, well, before you take a second, on the left-hand side, it will give you the information on that. So if you scroll over one of the circles on the map, it will tell you where it was, what the depth of the earthquake was, what the magnitude was, and its exact location. The next thing I want you to do is zoom out. So that way you can see a map of the entire world. Take a few moments and make a few observations. I want you to think about where the locations of earthquakes are, and go ahead and start thinking about if you can tell me what those red boundaries are along the map. Okay, so if you thought or said that those red line boundaries on the map are plate boundaries, you would be correct. Those lines represent the interaction of where our plates are. And what did you think the location of earthquakes were? Were they randomly placed, or were they concentrated in certain areas? If you said that they were concentrated along the plate boundaries, which are the red lines that are depicted on the map, you would be correct. So before we get into the plates, first we need to kind of have an idea of what our plates are made of. So our plates are a part of our lithosphere, and the plates are made of oceanic and continental crust, and that crust is made of rocks. And a rock is an aggregate of two or more minerals. And you have three different types of rocks. You have sedimentary rocks, which are rocks that are formed in a depositional environment where wind, water, ice, gravity has moved the sediment into a certain place and then compacted it, and it's then lithified. Igneous rocks are rocks that are formed from the crystallization of molten rock, magma if it's underground, and lava if it's above ground. And that magma and lava cools and it crystallizes and it turns into an igneous rock. And metamorphic rocks are a combination of both sedimentary and igneous rocks, and they form from existing rocks. So they take those sedimentary and those igneous rocks, push them deep down into the earth. With pressure and temperature, they heat that rock up and they change it into something different, which is a metamorphic rock. And depending on what state of the rock cycle the rock is in is what gives it its classification. So Earth's processes are what changes one type of rock into another through the geological cycle. So you have the hydraulic cycle, which is our water cycle. You have the rock cycle, and you have the tectonic cycle. And all of these work together to change the rocks into something different. This is a diagram of the rock cycle. So if you see, it doesn't matter where we start in it, we could start anywhere, but we'll go ahead and start with igneous rocks. If you start with the igneous rock and you form the igneous rock, the magma cools, it crystallizes, and then you bring it up to the surface of the earth. And at the surface of the earth, that rock is now exposed to other earth processes like weathering and erosion. That will turn that rock into a sedimentary rock because it's going to break that rock down into tiny, tiny pieces, or maybe larger pieces, or all different types of sizes of pieces, and it's going to turn that into a sedimentary rock. If the sedimentary rock is introduced to heat and pressure or different types of chemical processes, it will then turn it into a metamorphic rock. If that metamorphic rock completely melts and turns back into magma and then solidifies again, then that rock is now an igneous rock. So you can see how the rock cycle is interchangeable, and it's very dynamic, and it's constantly changing, and there's lots of ways you can change one rock type into another, and it doesn't just go in one direction. So let's go ahead and discuss Earth and its layers. So Earth has layers, and there are two fundamental ways to describe the interior of Earth. One is by her physical properties, and the other is by her chemical properties. So physical properties of the Earth, we describe that by the lithosphere, the crust, the moho, which is called the Mohovic discontinuity, the asthenosphere, the mesosphere, the outer core, and the inner core are all names that we give the layers of Earth based on physical properties. And the names of the layers of Earth that we give based on chemical properties are the crust, mantle, and core, which are probably the ones you've heard of or are most familiar with. So this diagram shows you what Earth's internal structure is like. And you see on the left-hand side, in between the diagram of Earth itself and the little pi wedge that's there, those are the chemical descriptors that we give to Earth. And you can see you have your solid inner core, your liquid outer core, your mantle, your moho, your asthenosphere, and then on top, your lithosphere. And the lithosphere is what we want to focus on for this lesson, because that is going to be where our plate boundaries are located. So, plate tectonics and the plate tectonic theory. Alfred Wegener is the father of plate tectonics. He is the one who introduced this, and the plate tectonic theory states that all of the continents used to be one, and using evidence like fossils and mountains and matching of rock types gave Alfred Wegener the idea that all these plates used to be one, and then they drifted apart. So our plates are moving, and they cause different things to happen. So what plate tectonics is, it's a large scale process which the plates of the Earth, which we call the crust, move and shift over the mantle. And the mantle is kind of, you need to think of it maybe like almost like a pudding or a jello. And then you can think of your crust like a graham cracker, and it moves over your crust moves over the mantle, and it creates different landforms on Earth's surfaces. So we have continents, mountains, ocean basins, volcanoes, islands, and ridges that are all created by the movement of plate tectonics. So how plate tectonics move, we classify them by how they move, and that's how they get their name. So you have three main types of tectonic relationships. You have divergent, convergent, and transform plate boundaries. So a divergent plate boundary is usually the players that are involved, and we'll call the players, I will refer to that, the plates as the players. So the players that are involved are mostly oceanic plates in divergent settings. And it is the spreading of two plates away from one another. So what happens here is one new crust is created, and you have the formation of a mid-ocean ridge. So if you could think about two plates coming together like this, and they spread apart, and what comes out of them is magma, and that creates new crust, and it pushes it away, and it forms what we have, the mid-ocean ridge. So some of the hazards that you get from that, so the formation of the mid-Atlantic Ocean ridge is what is a result of that. And you get light earthquakes and non-explosive volcanic eruptions. There's not a lot of activity when it comes to divergent plate boundaries. Now, convergent boundaries is where it gets a little more exciting. So the players that are involved in convergent boundaries, you have oceanic lithosphere and continental lithosphere. So you can have three different combinations. So you can have oceanic crust and continental crust. So when oceanic crust and continental crust meet along plate boundaries, one is subducted underneath the other. That means one plate, the heavier, the denser plate, is going to be subducted underneath the lighter plate. So in this case, oceanic plate is denser. It's usually, oceanic plates are older, and it will be subducted underneath the continental plate. And then what you get from that is the formation of continental island arcs and very deep trenches. A good example of this would be the Andes Mountains and the Marianas Trench. All of those are examples of what you would get from a convergent oceanic to continental plate boundary. So when you have oceanic crust and oceanic crust that meets, it's one again will be subducted underneath the other. So the younger oceanic plate will be subducted. I'm sorry. The older oceanic plate will be subducted underneath the younger oceanic plate. And what you will get from that is the formation of volcanic island arcs. This is a good example of this is what our Caribbean islands are. And then the third type of convergent plate boundary you have is continental and continental. So you have continental crust that meets continental crust, and what you get is a collisional event. This is what we call our mountain building events, or in geologic terms, an orogeny. And this will give you the formation of the mountains. Great examples of these are the Himalayas and the Appalachians. And just a little fun little fact is our Appalachian Mountains here along the East Coast were once at least the size or maybe bigger of the Himalayan mountains, but over millions and millions of years they've been eroded and weathered down, and now are the mountains that you see here today. So they are very, very old mountains. There is a lot of geologic history there, and it's a beautiful place to visit. The other type of plate boundary we have are transform boundaries. You could either have oceanic crust meeting oceanic crust, or continental meeting continental crust. And the idea behind a transform plate boundary is you don't really have collision or subduction. What you have are two plates that are sliding past one another. And what you get here is the result of that is some minor crustal deformation. And a great example of a transform plate boundary is our San Andreas Fault. So the two plates are moving, and one plate is moving north. So the Juan de Fuca plate is actually, the Pacific plate and the North Atlantic plate meet, and that's what creates the San Andreas Fault. And the Pacific plate is actually moving north at a very slow rate. All right, that concludes our lesson for today. Does anybody have any questions? Thank you guys so much for participating, and if you have any further questions, please let me know.